All right, welcome to the second session. My name is Joachim Neu. I'm a PhD student here at Stanford, and I'll be guiding you through the session. Our first speaker today is Ija Tang. Please come up on stage. Ija got his PhD from Georgia Tech and is now a professor at Syracuse University. And we're very excited to hear him talk about actually work in progress work, which is about comprehensive understanding of Ethereum mempool denial of service security. And the rules of the game are as usual. We have 25-minute talk and then 5 minutes for Q&A. If you have a question, please line up at the mic and then we'll call upon you. Have fun.
Yeah. Thank you, Johannes, for the introduction. Good morning, everyone. Great pleasure to talk about Ethereum memory pool security. My name, as introduced, is Ija Tang. I'm an associate professor from Syracuse University. So this is joint work with my students, Yibo Wang, Kai Li, and Wang Ningding. So let me start with giving a quick recap on how transactions are handled in Ethereum blockchain. Let's say a Web3 client who wants to send out the transaction to Ethereum blockchain. So the client will send the transaction to a blockchain P2P node. And nowadays, we know of the upgrade, Ethereum works on two different levels, execution layer and consensus layer. On the execution layer, the node will use a buffer buffer the transaction in a data structure called memory pool, and then it will propagate the transaction to reach the entire P2P network. Okay. And on the consensus layer, the node will retrieve transactions buffered in the memory pool to build and propose block. So once a new block, including the transaction, is proposed, it will be further propagated, validated, and then appended to the blockchain. So you can imagine in this pipeline, memory pool is a critical data structure. Okay? The denial of memory pool service will cause a global damage. So first, a block validator, given a denied memory pool service, a block validator will not be happy because it will not be able to retrieve legitimate transactions from the memory pool, and it will be forced to produce empty blocks. In the long run, the block validators will lose the revenue from legitimate transaction fees, and they will probably lose the incentive in participating mining or block validation. There is an incident that occurred like 2 years ago. The memory pool service in Ethereum testnet was denied. And in this screenshot that we take from Etherscan, you can see the timeline goes like upwards. There are multiple blocks produced. So below the first red dotted line, we are looking at the 3 blocks produced prior to the attack. You can see prior to the attack, the blocks include 51 transactions, 46 transactions, 77 transactions per block. So that's the regular, like a block utilization. And once the attack is mounted, the next 4 blocks, you can see there is only 1 transaction per block, 1 transaction per block, 0 transaction per block, and 1 transaction per block. After attack ends, the utilization per block is resumed back to normal. So if we look at how much revenue the block validators receive, at the time it was miners receive. So during the attack, miner revenue decreased by 99%. So this is definitely something that block validators will not be happy about. On the other end, Web3 clients will not be happy about a denied memory pool service. because they will not be able to transact. And their transactions, although sent out, will not be able to be included in the next blocks. So whatever the app they participated in will fail. So based on this risk, we formulated the following threat, what we call asymmetric denial of Ethereum memory pool service. So in this threat model, attack client sends crafted transaction to a remote victim node's memory pool. Meanwhile, that victim node receives regular transactions sent out by the like a benign Web3 client. Okay? So the goal of the attacker is to make the memory pool under attack unable to buffer unconfirmed benign transactions from regular users or Web3 clients. Is this threat realistic or how practical this attack is? In order to do the memory pool denial of service, a baseline design is send transaction, spam transactions. So because in most Ethereum clients, memory pool admit transaction based on fee. The higher the fee is, the high priority transaction will be admitted to the memory pool. So an adversary, let's say a naive adversary, will just send a bunch of spam transactions at high fee. The fees are higher than the fee of normal transactions. So normal transaction will be evicted. But this baseline design will not be very friendly to the attacker. It will cost quite a fortune for the attacker. And to some degree, it may not be as practical. A more realistic threat is what we call asymmetric memory pool DOS. In this case, we formulate that the attacker cost should be much lower than the damage on the victim side. More specifically, the fees of adversary transactions will be lower than the fees of normal transactions. So today, the only known asymmetric DOS is the detail attack, which the result was published 2 years ago in cybersecurity conference CCS. And recently, I come to notice there's another similar attack in the space. The detail attack follows a quite simple pattern in which the attacker sends out a bunch of invalid transactions, such as a future transaction in Ethereum, to evict normal transaction, pending transactions in the memory pool. Because it is the invalid transactions that are sent by the attacker, which are not included in the blockchain, so it doesn't cost the attacker anything, like a 0 Ether. But this pattern is quite easy to detect, and actually it is already fixed in the latest Ethereum clients, most leading Ethereum clients, as far as we know. So given this status quo, we pose the following open research problem. Are there any new and stealthy asymmetric memory pool DOS attack other than Deter and other existing ones that can evade the existing defenses adopted in today's Ethereum clients? In this work, we approach this research problem from 2 different angles, automatic vulnerability discovery and security verification. So given an Ethereum client, we want to be able to find if this client is free of asymmetric DOS attack or not. If it is, we want to present a formal certification over that. If it is not, we want to be able to find a concrete functional counterexample. In other words, functional attack against the tested Ethereum client. So this is a work in progress. And in terms of approach, our motivating observation is the following. Finding asymmetric memory pool DOS is a safety checking problem. First, we formulate memory pool eviction safety property, among other things. Basically, the idea is if a memory pool is safe, then it means that the transaction fee in any reachable memory pool state should be lower bounded. If such a lower bound does not exist, it can be easily exploited. On top of that, we built a memory pool model. We built an explicit model of explicit memory pool state. And on top of that, we implement state transition rules by non-admission policies. This process currently is done manually. Okay? For instance, in our model, we build admission policy based on transaction fee. As I mentioned before, the higher the transaction fee is, the high priority transaction will be admitted. Also, we implement the defensive policies adopted in today's Ethereum clients that is intended to mitigate the detail attack. For instance, such a policy will prevent the eviction of valid transaction in the memory pool by any invalid transaction. So we implement the model and the safety property in TOA+, and we run the TOC model checker with the bounded iterations to find either violations or present a formal certification of system security, safety. So if a violation is found, we extend the model level error trace into concrete attacks, and then we validate the concrete attacks on real Ethereum clients. So using our automatic tool, we are able to rediscover deter attacks on older version of Ethereum clients. On top of that, we also are able to find 12 new memory pool DOS-related bugs. So on the table here, you can see so we report all the bugs to the Ethereum Foundation, which governs the development of different Ethereum clients, including Geth, Nethermind, Aragon, and others. So most of them get confirmed, and some of them get fixed. So today I'm going to talk about one specific example of the new memory pool DOS attack or bug that we discovered and recently get fixed in Ethereum clients. So in this attack belongs to the category that we call turning-based eviction attack, and it belongs to the class of more stealthy attacks, in which the transactions are the adversarial transactions. In the beginning, it does not appear as an invalid transaction. It is a valid transaction, and then once it is admitted to the memory pool, it will be turned into invalid transactions. And such stealthy transactions can bypass the rule Ethereum clients use to propagate the transaction to other nodes. Okay, so in this sort of toy example, we are looking at two polys. On the left-hand side, we are looking at attack client. Right-hand side, we are looking at a toy memory pool, a victim memory pool of 2 slots. There are 2 accounts, Bob, the victim account, and Malloy, the adversarial account. In the beginning, the Malloy has 5 Ether in his account. So for Ethereum, a transaction is essentially a droplet, a quadruplet. It consists of 4 fields: sender, nonce, price or fee, and value, the amount of Ether being transferred. So in this work, we don't consider the data field or the field related to smart contract execution. And in this initial state, we are looking at the 2 transactions sent out by Bob. So transaction 1 has nonce 1, and the transaction 2 has nonce 2. So they are consecutive transactions. Both are valid pending transactions. Price-wise, they are with 3 GWei, and the value are both 1 Ether being transferred. So this is Bob's B9 transactions. And attacker node's goal is to evict these 2 transactions at no cost, or very low cost. So what attacker do is 2-step. First, the attacker sends out the 2 transactions, TX3 and 4. They are both sent by Malloy, the account controlled by the attacker. Again, the nonce-wise 1 and 2, the fee of Malloy's transactions are 4, slightly higher than Bob's transaction 3. And both transactions have Ether value 1. So if that transaction, these 2 transactions are sent to the memory pool, TX3 and 4 will be admitted to the memory pool because 4 is higher than 3. So if we take a pause at this sort of snapshot and look at how the attack goes, at this point, the dorsal attack has caused the full damage to the victim transactions because Bob's 2 transactions, TX1 and 2, have already been evicted from the memory pool. Okay? So in other words, the damage caused by attack is 6, 3 plus 3. But in terms of the cost by the attacker, it is 8, because at this point, these 2 transactions are both valid transactions, and they will be included into the next block. So 4 plus 4, 8 is larger than 6. So this is like a successful attack, but it's not a successful asymmetric attack. So what the attack wants to do is to lower down his cost. And this comes to the second step, in which attacker send TX5, a transaction that we call a turning transaction. TX5 has the same nonce with TX3, but the price-wise is higher. So it's a 5 GWei, then higher than 4 GWei. Value is 5 Ether instead of 1 Ether. Okay? So the memory pool will admit this transaction because of 2 reasons. One, it has a higher transaction fee, 5 larger than 4. Second, this is a valid transaction because 5, this is, does not go beyond the balance that Malloy has. Okay? So if we forget about the transaction fee a little bit. Okay? So this transaction will be admitted to the memory pool. Before the admission, transaction 3 and 4 are both valid transactions. I use this green arrow to indicate both transaction fees will be charged by the blockchain. But once TX5 is admitted to the memory pool, replacing transaction 3, this is what the memory pool looks like. TX5 is still a valid transaction, but admission of TX5 will turn TX4 from a valid transaction to an overdraft transaction. And TX4 will become an invalid transaction if the block validator is going to retrieve transaction from the memory pool at this point. It will not be able to validate the transaction or include it to the next block. So it decreased the attacker cost from 8 to 5. So 5 is smaller, lower than 6. So this constituted a successful asymmetric DOS attack. So this is how things work at a high level in this Toy Story. We also validated this attack by running the attack against the real Ethereum clients. We run 3 nodes in a local network. Attack node sending adversarial transactions, victim validator node reading transaction from its own memory pool and validating the next block, and workload node that generate benign transactions. And so from this figure, you can see once the attack, so x-axis looks at the essentially timeline, y-axis looks at the cost of different transactions. Once the attack starts, blue lines and red lines drops immediately to 0. What that means is the blue line represents the cost of benign transactions in the memory pool under attack. And the red line represents the cost of adversary transactions. Both lines are close to 0, which means the damage is maximized. Almost 100% of memory pool's content normal transactions are evicted, and the cost of adversary transactions also becomes 0. Okay? We compare this attack with the case where things goes well without any attack in the green line. So you can see without attack, green line, the benign transaction fee do not drop. Okay? We also compare it with the baseline span transaction attack. So you can see in terms of cost is more than 3 orders of magnitude lower than the baseline high cost span transaction attack. So overall, we measure our result by 2 metrics, more than 99% of success rate and also very low ether cost per block. So we have reported this bug to Ethereum Foundation, and we also developed a security patch. Actually, in April this year, this what we call turning by eviction replacement bug are fixed in Geth security release version 1.11.4. Okay? We are working in progress for other asymmetric DOS vulnerabilities in Ethereum clients. We are grateful for the support and the collaboration with the Ethereum Foundation team in terms of bug bounty and also academic grant program. So in this talk, I introduced the problem of or the security attack asymmetric denial of memory pool service. Also talk about the open research problem in the space, given the defense that is already taken. Formulate the problem by safety checking problem, and also present discovered attacks with both toy examples and also how it works in practice. With that, thank you for your time, and I'm happy to take questions.
Okay, great. Yeah, if you have questions, please use one of the 2 mics that are in the room. I'm going to ask a question myself, which is, you say this is work in progress, right, towards a comprehensive understanding of DOS, security and issues of the mempool. Where are we in this, process of getting a comprehensive understanding? Where do you, what are open problems? What are things that people should think about? What's your sentiment in terms of, can we actually get this provably secure, or will this always remain at the level of heuristics, etc.?
Thank you for the question. And this is also the question we have been actively working on, which means it is a hard problem. Is there an end in this arms race between attacker and the defense? For that, I want to say we envision this can be closed to some degree, but the fundamental challenge in this place is, in this problem space is the trade-off between, let's say, validated revenue optimization and the DOS security. So Imagine if you don't care about the revenue at all, then you can implement a very simple FIFO queue, right? So I just, everything that is admitted into memory pool, I'm not going to allow any eviction or dropping of the transaction. It's like locked over there. But that will not be very a good design if you want to optimize the revenue by the block validators. And once the eviction or other optimization, revenue optimization scheme is allowed, that will simultaneously create the risk of a DOS attack. So how things work out between these two ends, revenue optimization and the DOS attack, yeah, that's something we have been working on, and I think that's a sort of open problem in this space.
Okay, so it sounds like that it's only economically feasible if the attacker spends a lot of gas for these types of transactions. And then as like a follow-up question, it also means that in order to perform these attacks, you need to have searchers or nodes that understand the full state of the mempool, so you know what the ceiling is in terms of how much gas you should spend to evict certain other transactions, right?
Is it comment or question? Sorry.
My question is, you have to know what all the other transaction costs are in order to perform this attack economically, right?
Yeah, to some degree, yes. This is in the current design, at least in Ethereum, is memory pool content is publicly accessible. So it's an open membership network. So you just join the network, and you will the memory pool of your node will be populated. From there, you can sort of get a sense what the memory pool of other nodes in the network looks like. So yes, to your question, it's better you know what the content the memory pool holds before you send in an attack. I know there is like a private transaction in the space as well. So for that, this work does not apply to the private transactions.
Okay, thank you.
Thank you.
You talked about the trade-off between DOS security and revenue. Do you see that as like a fundamental trade-off? And if so, like what is the intuition behind that trade-off?
Yeah, thanks for the question. Yes, so to me, I do think that this is a fundamental trade-off because of the fundamental in the sense that the transaction model by Ethereum or other account-based blockchains. For instance, in this toy example, if you look at it, one of the vulnerability comes, the cause of the vulnerability comes from how the transactions are designed in Ethereum. Unlike the UTXO, where any account balance needs to be atomically spent in Ethereum, you don't have to atomically spend it. So you can split it into arbitrary number of pieces, and that's why we can send two transactions to spend this this account, and that's why we can do this to create this overdraft situation. So let's say in Bitcoin, I think this specific attack will not be applicable. So if you want to change, so that's one way you can change, and I think that's fundamental in terms of how Ethereum is designed, account-based blockchains. And also there are other things that pose challenges. If you think, so because memory pool, you have to make a decision online. You cannot wait after you buffer it and then do the optimization or admission in the offline manner. So you don't know what happens in the future, right? So whether or not to admit this transaction, you can only rely on the past history. The thing in Ethereum is that different transactions, they can have inter-transaction dependency. The transaction that arrives later can turn the transaction that admitted earlier into invalid transaction. So that's, yeah, that's something that needs to be looked at if we want to fix this problem altogether.
Great.
Thank you.
Let's thank our speaker one more time.
Thank you.
Then we have our second speaker of the session set up. Okay, our second speaker of this session is Kai-Hua Chin, who is a final year PhD student at Imperial College London, advised by Arthur Gervais. And he works on blockchain security with an emphasis on DeFi security, and today he'll be talking about the blockchain imitation game.
Thanks for the introduction. Yeah, my name is Kai-Hua. I'm going to talk about the blockchain imitation game. This is a joint work with Stefanos, Lee, Benjamin, Don, and Arthur. So it's not a secret that millions and billions of US dollars are extracted from the blockchain and the decentralized finance ecosystem from different sources like arbitrage, liquidation, and different kinds of DeFi attacks. This is also known as MEV. The entities who go on hunt for these MEV opportunities are called MEV searchers. Now, to become an MEV searcher is not an easy job. Thinking of if you are an arbitrager, and what you need to do is you need to monitor the financial market 24/7, try to identify the price difference across different financial markets, and once you identify an arbitrage opportunity, you need to issue an MEV transaction swiftly to be the first one taking this opportunity. Because, you know, these profitable opportunities are typically one time. And also, as a searcher, you typically need a contract. Here we have example, we have MEV contract, we have arbitrage function, and there are in total 3 financial actions. First, we swap Ether to USDC, and swap back USDC to Ether, and finally sends back the profit to the transaction sender. And the purpose of such a customized smart contract is to ensure that these financial actions are atomic, meaning all the actions should succeed or fail altogether. Because you know you don't want your arbitrage be interrupted by other blockchain transactions. Now, thinking of you are a lazy MEV searcher, you don't really want to monitor the financial market 24/7. You don't want to understand the complex trading rules of different DeFi protocols. You don't want to figure out how every smart contract works for these different DeFi protocols that are emerging every day, but you still are dreaming about making money out of this system. What would you do? Well, possible solution is you can become a copycat. You can literally copy the strategies from the others without thinking of your own strategy, right? And in our work, we call such a strategy the blockchain imitation game. So to understand what imitation is, let's dive into the life cycle of an MEV transaction. So first, the MEV searcher identifies the MEV opportunity and issues an MEV transaction. This transaction is propagated through the public peer-to-peer network or other private channels to be observed by blockchain miners, builders, validators, who are responsible for creating the next block. And this transaction is eventually executed and mined or included in the blockchain. So you might notice that from the observation phase to the execution phase, there is a small gap. This time window typically lasts a few seconds, actually opens up the possibility that an imitation player can observe a profitable transaction, copy-paste, and then front-run original one. So in summary, the imitation game boils down a strategy of observing, copy-pasting, and front-running. You probably know how front-running works in a blockchain system. Now the question is, how can we copy-paste? How can we generate an imitation transaction? So one very basic form of imitation strategy that we introduced in academic paper last year is called naive imitation. So to create a naive imitation transaction, an attacker basically blindly duplicates the potentially profitable transaction and performs some simple string replacements in the transaction data. Once the naive imitation transaction is generated, the attacker can simply verify the profitability by executing this naive imitation transaction locally. And if it turns out to be profitable, the attacker can then proceed with the front-running game. So let's look at a concrete example. We have a MEV contract with the up function. And you might notice that actually anyone who invokes this upcharge function can perform these upcharge actions, right? First swap Ether to USDC, then USDC back to Ether, and finally sends back the profit to the transaction sender. That basically means as long as the imitation attacker can front-run the original profitable transaction, the upcharge profit will be sent back to the adversary account instead of the original transaction sender, right? This is a very simple strategy that you can copy-paste any profitable transaction. Although it's very simple, but we find that it's rather effective. So we found that from December 2018 to August 2021, on Ethereum, the naive imitation strategy could have generated more than $35 million. That's not a small number, right? But fortunately, the naive imitation is quite easy to prevent. So the searcher can basically add one line of code in his or her MEV smart contract, checking whether the transaction sender address matches a specific value. Then in this case, if the naive imitation transaction is sent to this MEV contract, the execution will be immediately reverted, right? Because you cannot use the send account as the original transaction sender. So sounds great. Are we all safe? Is imitation still a problem? Well, apparently yes, right? That's why I'm here. It's still a huge problem. So if you look at this MEV contract and upcharge function again, you might realize what a smarter attacker can do is the attacker can create another MEV contract while bypassing the address validation, right? Because what is essentially for this upcharge transaction is the last three steps. Well, you only want to swap the asset and send back the profit. You don't want to really execute the address check in this smart contract. Well, this sounds very straightforward. I mean, if you can look at the smart contract, you can just copy the contract partially, and great, you can steal the money. But it's not that easy. There are still some challenges. Because what is executed in the Ethereum virtual machine is the so-called bytecode. It's not human readable. And the imitation protection mechanism can be anywhere in the smart contract. There can be even multiple smart contracts in one single transaction. So it's not that easy. So that's basically what we do in our paper. We propose a generalized imitation method. We call it ape. And ape allows you to automatically generate MEV transaction, but you can bypass all the imitation protections. So how it works? This is the overview of ape. I will discuss some of the technical details in my later slides. But on high level, the input is any pending transaction, and the output is the imitation transaction that includes all the contract deployment, also the imitation execution. So in total, we have 6 steps. In the first step, we executed the pending transaction locally. We build up the dynamic control flow graph. So for those who are not familiar with this concept, it's just some graphic representation of the transaction and the contract execution, showing how the different codes jump to each other among these code blocks. And then in the second step, we try to analyze the probability of this pending transaction. We try to identify the so-called beneficiary account who are receiving revenue in this pending transaction. Those accounts are the accounts that we aim to capture in our imitation transaction. Now, in the third step, we executed naive imitation transaction I mentioned earlier locally again, and we performed some dynamic intent analysis. And the purpose of this step is to identify all the code of imitation protection automatically across different smart contracts. And then the step 4 is the patch identifier, where we're trying to figure out all the smart contracts that we need to replace and synthesize in the imitation transaction. And then we synthesize these contracts. And then in the step 6, we validate the imitation adversary contract deployment and imitation execution locally again. And similarly, if it turns out to be profitable, the attacker can use the imitation transaction to front-run the original profitable one. So let's dive into a bit into the details. So first is the dynamic intent analysis. So when you look at the contract with imitation protection, so why does the naive imitation fail from a bytecode perspective? Well, it starts with actually some small differences, right? So in this case, we have a different transaction sender, and such a difference propagates through the execution and finally reaches a so-called conditional jump in the bytecode. So specifically, it's called jump high. And from this conditional jump, the execution of the imitation transaction will jump to another branch. As a result, the original transaction will continue with the upcharge operations, while the naive imitation transaction will be reverted, right? So the purpose of dynamic intent analysis is just to track the operation code that may introduce a difference in execution, and trying to find where the code start to go into a different branch. So in this way, we are trying to figure out all the imitation protection mechanisms in the MEV contracts, in this case. So the next is the patch identifier. So to understand what patch identifier does, let's assume the following scenario. So in this case, the MEV contract is not invoked directly by the transaction sender, while it's invoked by another contract, let's say contract A, and we have a function E that calls MEV.up xy, right? So in this case, let's assume we can successfully identify the MEV protection in the MEV contract, imitation protection in the MEV contract, and we successfully synthesize an adversary contract that bypasses this protection, and we deploy it. But the imitation execution may still fail, right? Because as you know, as you can see, the address of the MEV contract is hard-coded in contract A. So now when the adversary sender is trying to invoke the contract A, the contract A will still call the original MEV contract instead of the new one that we just deployed. So what we need to do here is we need to deploy another contract, A prime, and we should invoke the MEV prime properly in this case. So patch identifier is basically such a recursive process that we are trying to identify all the smart contracts that we need to replace and synthesize in this MEV game. Okay, so finally, we have the contract synthesize. So as we just discussed, we are trying to follow the execution of the original profitable transaction, right? But there is some differences that leading to, in some scenarios, the jump high condition might lead to a different branch. So in the contract synthesize, we need to take care of such differences and try to force the jump high to follow the original path. So what we need to do is we need to just simply delete the conditional jump in the smart contract, and we replaced with unconditional jump. We call jump in the EVM bytecode. And in this way, we just force the jump to follow the original path. We call it the jump by forcing in our paper. And also, we need to take out some other components when we are trying to synthesize the contract. For instance, we need to, as I just discussed, we need to make sure that every synthesized smart contract should be invoked properly. And also, every newly deployed smart contract has an empty storage, so we need to recover the storage properly in the synthesized smart contract if necessary. And also, in some scenarios, the MEV searcher may leave the money or the profit in one of the smart contract. But when we synthesize a new smart contract, we actually have no way to withdraw the profit later on because that part of the code is not touched, and we didn't include any such of logic into our newly deployed adversary smart contract. So in this case, in the imitation, we are trying to involve so-called asset transfer redirection and send back all the profit immediately to the adversary sender within the imitation transaction. All right, so to understand the effectiveness of APE, we performed a comprehensive evaluation by executing APE on every past transaction from August 2021 to July 2022 on both Ethereum and the BNB Smart Chain. And it turned out APE could have generated more than $148 million on Ethereum and more than $42 million on BSC. And we also performed some real-time evaluation by injecting the APE logic into a running mainnet full node without actually sending out the imitation transaction from ethical consideration. And the performance of APE is great. As you can see, on average, every imitation execution only takes 0.07 seconds, which is way below the block interval of Ethereum and BSC. Okay, so now if you look at the accumulative profit diagrams I put in the slides, you might notice that there are some spikes along with the line, right? For instance, in December 2021 and on Ethereum and April 2022 on BSC. So to understand where the revenue comes from in these high reward transactions, we did some manual investigation. And it turns out many of these high reward transactions are actually these DeFi attacks, where attacker basically exploit some vulnerabilities in smart contracts or DeFi protocols, trying to profit by stealing money from other benign victim DeFi users. So such insights actually leads to an interesting proposition. Can imitation attack be repurposed as a defensive mechanism? Well, the answer is perhaps yes, right? So imagine that you are a miner or you are a validator. When receiving a DeFi attack transaction, instead of including this transaction in the block immediately, you can generate a counter attack by using our imitation strategy and then front run this DeFi attack transaction. And then later on, you can deviate the money into your own pocket, and later on, you can just return the profit to the victim DeFi users, right? Acting as a white hat. So in our evaluation, we find that on Ethereum, APE could have prevented 29 attack transactions, corresponding to more than $73 million of users' loss. And on BSC, the preventable attack transactions reaches 40, and the user's loss reaches more than $22 million. So I have also listed several examples for you to reference in the slides. So with that, I'm going to wrap up my talk, and I hope you find it interesting, and I'm happy to take questions.
I'm sure people will have some questions. If you want to ask a question, please line up at the mic. I'm curious, I'm sure these kind of attacks are already in maybe some more primitive form happening in the wild. Can you maybe speak to, in your experience, based on what you've seen on chain, how sophisticated are these kind of copycats at the moment, and what techniques do they employ?
You mean the wild, right?
Yeah.
We haven't observed any one is using our strategies by since a smart contract on the fly and trying to merge everything into one transaction. But we do observe some ME researchers trying to play this imitation game beyond the naive solution. What they do is typically sometimes they trying to extract some effective actions, financial actions, trying to include in one MEV transaction and try to front run the others. So I mean, in summary, all the transaction execution is public, and there can be many ways that how you can copy a transaction. So I'm pretty sure there are many solutions, but some I'm just not aware of.
First of all, thanks for the great talk. Starting from the intuition of using this imitation game as a defense technique against DeFi attacks. First question, can you give us a sense about how many attacks, percentage-wise, can be intercepted out of the DeFi attacks that you have analyzed using your technique? And the second question is, how easy or hard is it for an attacker to bypass your defense technique then? If I know how your imitation pipeline works, I guess I can shape the contract in a way that it does not get detected. So can you give us a sense on that?
So first question is about percentage. So I would say theoretically all the single transaction attack could be potentially prevented by imitation. This is just because all executions are public, and so attackers basically use a sequence of DeFi actions to exploit some money from the users. So I don't have the concrete number about the coverage of our solution against all the DeFi attacks, and our implementation might have some bugs, might miss several transactions in our evaluation. But I would say, theoretically, we can prevent every single transaction DeFi attack use this solution. And regarding multiple ones, there can also be solutions that you can imitate multiple transactions, but we are working on it, basically. What's your second question?
How hard is it for an attacker to bypass your technique once the attacker knows how your pipeline internally works? Can the attacker simply craft a contract that is shaped in a particular way that is not intercepted by your technique?
Yeah, I mean, this is a cat and mouse game, right? So attackers, for sure, we are trying to obfuscate their attacks, for instance. We're trying to find out some optimization solutions to prevent our imitation strategy. But as I just discussed, right, everything is public. So what you need to do is just to copy the effective actions of what the attack is doing and try to create a counter-attack. So I would say it will be hard, but it's not impossible, but I don't have a solution at the moment in my mind.
Thank you.
I had just one question. It's a great talk you gave. Can you please go back to a few slides behind? I want to show the two codes, 0x12. Go further behind, please. One more.
Which
maybe.
one?
Yeah. Yeah, this one. I think, no, it was the previous one. One more, I think. Yeah, this one, yes. So how did you know that if you inserted the 0x12, this is a vulnerable function that you decided to work on this? Did you use some tools and scan some other applications to come to a conclusion that this is one possible function that could result in the problem? That's one part. And the second part is, can we always say that a kind of a fix to this is to replace this jump I and push with a jump I and a pop and a swap and a push and a jump, and that will fix this problem? Can we generalize it for this kind of bytecode?
I'm not sure what do you mean by generalized bytecode.
Okay. No, I was looking for a general solution. Can we replace if we use this? So we can go 2 slides later in the front.
I mean the
Yeah, this one. Yeah, this one.
part. Okay.
So this is the fix, isn't it? Isn't this the?
Yeah. So basically, because we only have 2 scenarios to take care of, so JumpI only has either jump or not jump. So here I give you an example how we can force it to jump, and in the paper we have another scenario that how we can force it not to jump. Right. So in this case, it just delete the jump, and it can just continue to execute.
Yeah. Thank you.
Great. So this concludes the second session. We have a break now. I think you can find lunch outside. Thank you.